When you've been in the IT business for a while, you have stopped running out of things. We used to run out of memory. Well, unless we're doing HPC, high performance computing, we don't run out of memory these days. We used to run out of disk, we used to run out of computing power, and the evolution of the field has been so amazing that we stopped running out of constraints. But one thing I'm starting to run out of is adjectives, superlatives. Okay? We used to try to impress our students by saying, you know, in my pocket nowadays I have more computing power than the biggest, the most powerful computer in the world when I started. It impressed them or not, but we've done this for so many years that now we have exhausted the supply of superlatives of the English language, which is finite. And new stuff keeps coming up absolutely all the time. So, for example, as is already clear from the other speeches, from the other talks here, we have 5 directions that are changing the world, not just the scientific world and the technology world, but the world in general. The new artificial intelligence, big data and machine learning, which has already been emphasized, cybersecurity, on which I'm not going to talk because other people here are much more qualified, cloud computing and DevOps. If you don't know what DevOps is, I'll explain, and large-scale software engineering. So I'm going to present some of the developments that are going on in those areas, and I'm going to do it from a particular viewpoint. I'm a software engineer. I don't just mean a professor of software engineering, but I'm a software engineer. I write programs and I talk about programs, so my perspective is a software engineering perspective, certainly different from what you would get, for example, from a graphics person or from a theoretical computer scientist. So I'm going to emphasize the contribution of software engineering to these techniques, to these new advances, the need for software engineering, but also the contribution of these new techniques to software engineering. As Sergey pointed out, the world rests not only on computers, but on software. I'm going to show you some of the software that actually runs the world, literally. Let's start with AI. So for some people, hearing big speeches about AI triggers a kind of cynical reaction. Well, we've been there before, right? In the 70s, everyone was excited about AI the way people are now. And we had this kind of thing, which was impressing people for a while. This is a kind of semi-serious development, but it was very much discussed. This was ELIZA, which was a program that impersonated a psychologist. And the reason people found it exciting is that it came close to passing the Turing test. You know, that is to say, some people were not able to recognize whether at the end of the line it was a psychologist or a human psychologist or actually a computer. Now, this was logic-based, or not just ELIZA, but this early research in artificial intelligence, and it was also rules-based, okay, on human input. So you want to write a program to diagnose cancer, well, you go to oncology specialists, and based on their input and on their experience, you put in rules which say, in this case it's cancer, in that case not, and the tumor looks like this, do this, otherwise do that, and then it becomes complicated because the rules conflict, so you have to give orders of precedence to them. And the best that can be said about that kind of approach is that it failed. You know, they oversold. And at some point the world came and said, well, you promised us the moon and you didn't deliver anything. And then 30 years later, it comes back. I would say it's the revenge of the flies. Okay, I'm referring here to a book by Maurice Maeterlinck, a Belgian poet, the librettist of Debussy's Pelléas and Mélisande. So he fancied himself as an entomologist, and he wrote a book about the life of the bees. And he said this, I've never been able to find out if it's true or not. You take a bottle, you put a few flies, a few bees in it, also a few flies, and then you bring a lamp. You bring some lighting on the other side. And so the bees, and you have to notice that this is an audio-visual presentation, right? I think it's the first audio-visual presentation in the history of SIT. The bees are attracted by the light, so they're going to stay there, okay? So the bees are smart, right? They know that the exit is usually the place where the light is, okay? And the flies, they absolutely don't have a clue. So they fly in all kinds of possible directions, and if you wait long enough, you're going to see that the flies actually survive, they get out, and we're not going to wait that long, but at some point the bees all die, okay? And this is very much modern AI. I mean, old AI was very much bee stuff, okay? You try to do the smart thing. And new AI is very much fly stuff. So I don't want to insult the new AI people, because actually there's a lot of intelligence, for example, the great work that received the Turing Award this year in deep learning. So of course there's an incredible amount of intelligence there, but very much it's fly stuff, and what has changed is something that was also referred to by Dr. Real a few moments ago, that is to say is the compute power and the amount of data that we can have. So if you have millions of pictures of dogs and millions of pictures of cats, and of course a good theory behind, a general theory, not a theory of cats and dogs, but a theory of Bayesian statistics and deep learning and so on, well, this problem is still relatively open. But for example, a number of problems which used to be central problems of computer science, like character recognition, this is basically solved and largely solved by these techniques. Another example is Google Translate. You know, when Google Translate and the similar tools came into the scene, everyone was absolutely bedazzled, dazzled, right? You went to a Korean site, you know, assuming a language that you don't know, and you could find out what it was talking about. And, you know, it's very much it's very much fly stuff. You know, you put enough, you go to the European Union, which has all these texts in many languages, and you put enough of these texts in French, English, German, and so on together, and at some point you'll see the correlation. So for example, you see here, meine Tochter liebt mein Vater, and it translates it into English. So now, the other way around, meine Vater, no, okay. Liebt meine Tochter. Okay. Okay, it's still doing it right. Okay. And then, okay, let's achieve. Be mischievous for a while. Well, okay, and I think anyone who is a German speaker knows that it's actually the other way around, right? Here. And it's not such an artificial example, right? It could be meinen Vater heißt mein Sohn, aber, and so on, right? So this is B stuff, right? This requires classical linguistics and analysis and structure and theory. So it's getting better all the time, but because actually they're cheating, they're introducing a bit of B stuff into this. Now, software engineering is as needed in those areas as it is anywhere else, because major problems remain. Right? How do you justify the results? Imagine, for example, that you have a lawsuit which is decided with the help of such algorithms. And this is not science fiction. It happens in the US already. Well, at some point, maybe not in the US, but in Europe, certainly you need to be able to justify the result. You know, if the program tells you this guy is guilty, that guy is innocent, well, the lawyers are going to demand some explanation, and current algorithms are not very good at that. How do we know that the correctness, that the algorithms and their results are correct? This notion of correctness of machine learning algorithms in particular remains open. Avoiding the reproduction of current biases. You know, you want to decide how to accept or reject credit applications. Well, maybe if you have a zillion existing cases, maybe they were biased by the people behind them. So how do you avoid reproducing the same biases again and again? Dealing with cases with very small data records. This hits home. I have someone in my family, a young person who was sick, very, very sick and was going to die. That was clear, and she was very tired, and all the physicians were saying, well, just get some rest. And finally, a doctor at the University Hospital in Zurich found that it was a disease of which there had been 5 cases recorded in the history of Switzerland. Okay, 5 cases. Now, Switzerland is not very big, but still, okay? So how do you go in the fly kind of approach? How do you approach this kind of situation? And then ethics. Let me give you an example of ethics. You know, it's something from an online forum from a well-known computer scientist, Henry Baker. And think, you know, 2015, right? The Volkswagen scandal, right? Consider a software model that basically mimics an emissions test. Okay, we put the systems through millions of lines of learning, and it will eventually notice that in certain conditions, you can optimize. Okay, and these conditions happen to be exactly the ones during which it's being tested for EPA standards. So it's going to come up basically with the algorithm that the great Volkswagen engineers, some of whom are probably in jail right now, concocted. So in their case, it was evil, right? So are we going to put the algorithm in jail? It's a learning algorithm. It just learned from experience. So this is just an example of the numerous ethics problems that we have thanks to these fundamental evolutions. Now, software engineering is needed because we deal with large stuff. So I used to try to impress my students in the first week of the introduction to programming course at ETH by showing the evolution of numbers of lines of code of operating systems. You know, Windows is 50 million lines of code, starting with there. You know, it started with 10,000 with the original versions of Unix and 3 million for original version of Windows. And Debian, Linux, so it's not just Microsoft, right? And at some point, I couldn't make it fit in the curve. So you can see that here it stops at 2006 because at some point I stopped trying to follow. But then you take Google again, 2 billion lines of code. Think of it, what it means to have 2 billion lines of code. So, you know, to give you an idea, 100,000 lines is something that one person can manage. My stock, if you like, is the stuff on which I built much of my work is about 3 million lines of code, the Eiffel Studio code base. And if it's well organized, you can have maybe not one person, but 2 or 3 people who together more or less understand what's going on. 50 million lines, this is already impossible, and think of 2 billion lines of code. So that's the kind of thing we deal with, and it's fair to say that on the software side, not on the computer side, but on the software side, we software people have produced and dealt with artifacts which are bigger than anything any other engineering discipline has produced. You know, think of, say, a complex plane, the A380, you know, something like this. It's big, it's complex, but nowhere close to that. And the only analogy that one can find is human systems, like a city, you know. That's more or less at that size, maybe not the billions, but certainly the millions. The difference, though, is that these are human systems which are supposed to be flexible and imperfect, right? If something goes wrong somewhere, and there's an accident here in the city, something that doesn't work, the system more or less recovers. In computing, we cannot afford this, right? Sometimes we can indeed shut off half of the code and it still works, but sometimes you change just 1 bit in Windows and nothing works anymore. So you have this, the mixture of this extreme complexity and this extreme demand on correctness and precision, which is really similar only to mathematics, okay? So same thing for cars, you know. Today's cars have hundreds of million lines of code, and of course, sure enough, the bugs are coming, right? 15% of bugs now to be blamed by recalls, for recalls. Something else that happened in this year is the other way around, the influence of AI and machine learning on my field. So software engineering has changed in a major way in recent years because it has applied to itself the techniques of machine learning and AI, of big data processing. And what has changed is that you have these code bases that go on maybe 30 years in some cases, on which every commit, anytime anyone changes anything, this is recorded. Anytime there's a bug, it's recorded. Anytime the bug is fixed, it's recorded. So this has enabled research to answer questions like these. In Windows, for example, are more tested modules, the modules that have been tested more, are they more buggy than others or less buggy than others? Well, most people, I think, would think more buggy, or I'm sorry, most people will think less buggy because they've been tested more. It's the other way around, okay? The more tested modules are the more buggy. Why? It's because everyone knows they're buggy, so we keep testing them, but they're junk in the first place, and garbage in, garbage out. Another example is complexity of a module a good predictor of its number of bugs? No, they're much better predictors, like number of times this has changed, but it can be a very simple module or a very complex module that has no visible effect. And one last one, in a big software product like Eclipse, do bugs come mostly from beginners, novice programmers, or from experts? They come more from experts, because when you have a novice coming into Eclipse or Linux, everyone checks, first he does things at the periphery, okay, which are not so critical. And second, everyone checks what he does. When you have Linus Torvalds changing something in Linux, the author, first is typically very hard, and if it doesn't work, it has really bad consequences. So I think I'm running out of time. Let me go to a couple more points, and then I'll, but one of the things that we do in our field is proving programs, okay? Which is one of the most vibrant areas of development. Let me give you an example here. If you try to travel in Paris at the moment, it's an absolute catastrophe, except for two lines, line 1 and line 14. Why? Well, you can guess it. They're automated, okay? So then computers don't go on strike. But the proof of the system that actually automates line 14, which was the first one, is a few tens of thousands, about 30,000 of individual steps, which is bigger than any standard mathematical proof. And of course, it was verified automatically. So this is the kind of thing that we do. So let me just conclude with a comment that is ascribed to a very famous computer scientist. He's kind of the Moses of computer science. He looks like Moses. He looked like Moses a bit. And I haven't talked about computers, but because he was right. Computer science is no more about computers than astronomy is about telescopes. Computer science is more about this kind of thing. All these fundamental concepts that really make up the software science, the science of software, and which are really pregnant in our discipline. On the other hand, it's becoming clear that Dijkstra was wrong. At least he's going to be wrong in the future, because with quantum computing, computers become the subject again.
Thank you very much.